Welcome to another exciting video brought to you by Vision Concept Academy. In this video, we'll be looking at electric field and we'll be seeing electric forces between two charges, and we'll explain electric field intensity, plus some exciting examples where we dive into calculation. So sit tight and enjoy the video. Ensure you subscribe if you're not yet subscribed, and like and share for others to follow. So actually, electric field is a regional space where a charge experiences an electric force. And Coulomb is a scientist that studied this force, and he came up with the Coulomb's law that states that the force of attraction F between two charges is directly proportional to the product of the charges and inversely proportional to the square of the separation, distance of separation. Okay, so this formula defines this Coulomb law. Coulomb is a scientist that, like I said, studied the concept of charges. A charge can either be positive or negative charge, Q positive or Q negative. These are charges, and their unit is in Coulomb. So the force of attraction between the two of them, when you have two charges, either is that the polarity is the same. If the polarity is the same, that means there is a force of repulsion, because unlike charges repel. So if I have plus plus or minus minus, so because they are the same polarity, they will repel. They will repel themselves. Both of them, in these cases, will repel themselves. But if they are different polarities, unlike polarity, they will attract. So either repulsion or attraction, there is a force that is existing in them. So Coulomb studied this force and came up with a law that says that the force of attraction or repulsion between two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance of separation. So I can come here and define these parameters. Say where F here is either the force of attraction or repulsion, and Q1 is the quantity of charge for the first charge, which is measured in Coulomb, that is C, and Q is also the same thing here, quantity of charge of the second charge measured in Coulomb. I don't have to repeat this one, but let me just repeat it for. Then R is equal to the distance of separation measured in meters. Distance of separation between the charges. Okay, so we'll actually see distance of separation. So we'll actually see the where we'll have to solve this with practical application. Okay, so from here, if we remove this functionality constant, that is this functionality constant, and we introduce our equal sign, K is a constant of functionality, and K is defined as 1 over 4 pi epsilon naught. Epsilon naught is called permittivity of free space. It's a constant. Permittivity of free space. And the value of that constant is 8.85 times 10 raised to the power minus 12. 8.85 times 10 to the power minus 12. Normally, if you compute all of this, it will give you 9 times 10 to the power 9 Newton meter square and Coulomb square, like this. Coulomb raised to the power minus 2. Yes, that's what you do. Okay, so I have a question on the board, an example, just to apply what we have, the concept we have defined. The example says find the force of repulsion between two protons of 1.6 times 10 to the power minus 19 coulomb each if the distance between them is 5.3 times 10 to the power minus 11 meter. Take 1 over 4 pi epsilon naught to be this constant, 9 times 10 to the power 9. Okay, so Coulomb law is F is equals to K Q1 Q2 over R squared. Okay, so from here we are looking for force of repulsion. Why is it called force of repulsion? Because the charges involved are protons. They are both positive sign. They are both positive. The charge involved is proton, so they are both positive. Okay, so we are looking for force of repulsion. We are given that the proton charges are this each. So Q1 is equals to Q2 is equals to 1.6 times 10 to the power minus 19C. Okay, and then the distance of separation R is equals to 5.3 times 10 to the power minus 11. Okay, in meters, and the K, this constant K is given as 9 times 10 to the power 9 Newton meter square equals Coulomb per Coulomb square. Okay, so at this point, I'll just plug in my values. So this is K. K is, that is K. This is K. K is 9 times 10 to the power 9. I will leave the unit for simplicity. Then Q1 and Q2 are the same thing. So I'll have 1.6 times 10 to the power minus 19 all square. Okay, all over separation 9 times 10 to the power 9 all square. Okay, very good, very good, very good, very good. Very good. Okay, there's a challenge. Sorry, this is not this. This is R 5.3 times 10 to the power minus 11 all square. Yes. So by the time you compute this with your calculator, what you should be having is 8.2 times 10 to the power minus 8 Newton. 8.2 times 10 to the power minus 8 Newton. So this is the force of repulsion between the two charges. Okay. Okay, so we have a question on the board here. It says three charges. That is 1, 2, 3. Three charges, 10 plus 10 coulomb minus 20 coulomb and 16 coulomb. And 16 coulomb, okay. Okay, that 16 is minus. That's why I'm having minus here. Okay, minus 16 coulomb are distributed as shown below. Find the resultant force acting on the 10 coulomb charge. So now, you know, we looked at Coulomb's law, and we sampled just two charges, and they said part of attraction between the two charges and everything. So when we have three charges like this, so we're going to do a resolution whereby we will look for the force of attraction between these two, because this is positive and negative. So we have to look for attraction between these two, and at the same time also look for attraction between these two. So that the components, this one now, this force between these two, we'll call it F1, and the force between these two, we call it F2. So we'll have two forces from this point acting in two different directions, but at right angle to each other. So I can start by saying F1. F1 is equal to K dot Q1 Q2 all over R squared. Now, just follow me. F1 is this one. So F1 is equals to the K is what? 9 times 10 to the power 9 times Q1 for this case. For this case is, let's take Q1 as 10 times 20. The minus here is just to show that it's a negative charge. Don't put it inside this equation or formula. The distance of separation is 3 square. That's 3 square. Okay, that's 3. Then all square in the formula. Okay, so by the time you compute this with the calculator, F1 actually will give you a value it will give you 2 times 10 raised to the power 10, 2 times 10 raised to the power 11 Newton. Yes, 2 times 10 raised to the power 11 Newton. That's what F1 will give you. Now, F2 is the force that will act on these two charges. So I'll come here, I'll say F2 again is K, Q1, Q2 all over R squared. So we're looking at these two as a case study. Um, K is 9 times 10 to the power 9 times Q1 again is 10, Q2 is 16. Like I said, don't put the minus because it shows us that it's a negative charge. The separation distance is 2, but R is equal to 2. All right, so F2 will now give us from computation, F2 is 3.6 times 10 to the power 11. 3.6 times 10 to the power 11. 11 what? Newton. Now I have to this force, so I can redraw a vector showing these two forces. F1 is this one. This F1 is this direction. F1 is let me just put it here. 2 times 10 to the power 11, and F2 is F1. F1, yes. Then F2 is what? 3.6 times 10 to the power 11. So to find the resultant will now be this hypotenuse. So we're going to be using uh, the Pythagoras theorem. Yes, Pythagoras theorem. So I can come here, R. So R, I'll call it FR, resultant, is equal to the square root of 2 times 10 to the power 11 all square plus 3.6 times 10 to the power 11 all square. So let's complete everything here. So the resultant is, by the time you do this and this, you add, then you find the square root, you'll be getting 4.12 times 10 to the power 11, 4.12 times 10 to the power 11 Newton. So this force, this net force, we call it net force or resultant force. This net force is representing these two that are facing two different directions. F1 is due to these two charges, and F2 is due to these two charges. So we cannot just bring the two of them because they are acting in separate directions. So we can just get the net force, which is this. But the direction of acting, it should be acting on this direction. This direction. That is on the positive x-axis. All right. So the resultant is the direction of the resultant is this angle here, theta. The angle that this resultant is forming with the y-axis. And to get it, we'll use tangent of this. To get this angle, we say opposite over adjacent. So tan theta is equals to opposite, which is F1, over adjacent, which is F2. Okay? And theta, the angle theta, is the tan inverse of that ratio, F1 over F2. So theta, which is direction of the force, is equals to tan inverse of the ratio. F1 is 2, open bracket, 2 times 10 to the power 11 all over 3.6 times 10 to the power 11. So that theta, by calculation, will give us 32.28 degree. So this is the resultant force, and this is the direction it is acting. This force is acting at this direction, to the positive y-axis. So that is for the second example under application of Coulomb's law. So we'll move on over to electric field intensity and electric potential. Okay, so we'll go on to this subtopic: electric field, electric intensity, and electric potential. So electric field is defined as the region where electric force is experienced by a charged body. So electric field is a region where electric force is experienced by a charged body. That's the first definition. And the electric field intensity, you can either call it this one or you can call it the strength of electric field. You can either call it electric field intensity or you call it the strength of electric field. So actually, it is just like any point that uh, you have force, you know, applying to a unique charge. Any point. So it's just like saying force applied per unit charge. Per unit charge. Okay, so this one has a formula expression. So I can say electric field intensity E is equals to force on a unit charge. So this one has a formula. Okay, I can go down and break this one because there's a relationship between this one and what we just did before. So this is called electric field intensity E, like this. Or I can use big E to explain it like this. Okay, so you recall that force by as described by Coulomb. Recall, let me put it there. Recall, just remember that force is actually equals to K Q1 Q2 all over R squared. So if I put this in this equation, I have E is equals to this force now becomes K Q over R squared, whatever Q it is, dot 1 over Q. One of the Q is what is being affected here. So if I cancel this and this, what I now have as E is equals to K, then Q over R squared. So this is another formula for electric field intensity. Okay, so this is the relationship force per unit charge, force acting on the unit charge. But when you now remember that, okay, force is expressed as the relationship between two charges, product of two charges, and the inverse of their separation square, then you can bring this into this equation and you now get this. Okay, so that is what electric field intensity is all about. And on the other hand, electric potential is defined as the work done in bringing a unit positive charge from infinity to the point against the electric field. So I'm going to leave that, I'll come to that later, so I can work on this concept properly. So I'll give you some examples where we do some calculation and we'll come back to wrap up this lesson. Okay, so we have on the board two similar but opposite charge, two similar but opposite point charges, minus Q and plus Q, each of magnitude 5.0 times 10 to the power 8 minus 8 coulomb, are separated by a distance of 8 cm as shown in the vacuum. So this one and this one, there are two magnitude of charge, but opposite charges. This is 8, this is 5.0 times 10 to the power minus 8, and this is the same thing, 5.0 times 10 to the power minus 8. Yes. So, and they are both separated by 8 cm. But in this diagram, we are shown that the 8 cm, 5 of it is between Q and P, that's minus Q and P, and 3 is cm is between P and plus Q. So they said calculate the magnitude and direction of the resultant electric field intensity at point P. So this is the point of reference. Draw the lines of force due to this system of charges. So take K as 9 times 10 to the power 9. You know the units. We don't want to go through that. But then we'll look for the formula for electric field intensity is K, just one charge over R squared. This is the formula for it. So if I were to find the electric intensity of on point P due to this, is going to be, I will say E minus, because it is a negative one, because of this one, is equals to K is 9 times 10 to the power 9 times Q is 5 times 10 to the power minus 8 all over 0.05 square. Why am I using 0.05? Because I have to convert 5 cm to meters. Okay, so I'm going to get this one. I'm going to get this one. So E minus by computation will give me 1.8, yes, 1.8 times 10 raised to the power 5 Newton Coulomb. 5, then Newton per Coulomb. So that is the positive, that is the negative E. The direction of the intensity of the field will be going this way. Why? Because this one is positive, because of this, and it is going towards this side. So that's for the direction. We are just trying to say draw the line. So this is where the line is. Okay, now for the second one, which is the positive arm, that's this one, the force, the field intensity on P due to Q, positive Q, is E positive is equals to K Q all over R square. So E positive is equals to K. K is 9 times 10 to the power 9 times Q there is still 5 times 10 to the power minus 8 all over. This time around, I'm using 0.03 square. Why is it 0.03 square? Because I'm converting 3 TM into meters. Okay, so E positive will become 6 point, sorry, 5 times 10 to the power 5. 5 times 10 to the power 5 Newton per Coulomb. This is the unit for electric field intensity or field strength. Okay, so I've gotten this and this. So the resultant will now be addition of the two of them. E will now be 1.8 times 10 to the power 5 plus 5 times 10 to the power 5. So final answer will give me 6.8 times 10 to the power 5 Newton per Coulomb. So this is the resultant electric field intensity. The field is directed towards the left, because they are both directed towards the left. This one is directed towards the left again. Why? Because I have positive here, repulsion goes this way. So they are both acting towards the left. So I hope this video has been informative for you, and I'd like to thank you for viewing.